Somewhere in the darkness between galaxies, a dying star briefly becomes brighter than everything around it combined. For a few silent seconds, it releases more energy than our sun will produce across its entire lifetime. And then, it vanishes, not with the slow fading glow of an ordinary supernova, but with a focused beam of radiation so violent that it can rewrite the chemistry of space itself across thousands of light years. Tonight, we are going to explore what truly happens when the universe creates a gamma-ray burst, and what those colossal jets do to the worlds unfortunate enough to stand in their path. And if you've ever wondered what would happen if a black hole wandered through our solar system, you may remember another quiet journey we took together here on Velarin. Because strangely enough, both stories begin with the same idea: gravity concentrating unimaginable power into impossibly small regions of space. Welcome back to Velarin's Sleepy Space Mysteries, where tonight we drift slowly into one of the most terrifying and beautiful phenomena in the known universe. A phenomenon so energetic that astronomers once believed their instruments were malfunctioning when they first detected it. A cosmic event capable of tearing apart atoms, sterilizing planets, distorting magnetic fields, and leaving glowing scars across interstellar space long after the original explosion has faded away. But before we descend into these distant cosmic catastrophes, take a quiet moment to subscribe, leave a like, turn on notifications, and perhaps join the channel membership if you enjoy these long journeys through the sleeping universe. And while you settle in tonight, let me know softly in the comments below. Where in the world are you watching from tonight? Now dim the lights a little further, settle into the silence, and imagine a star so massive that when it finally dies, the universe itself seems to recoil from the violence of its collapse. Most stars spend their lives in quiet balance. For millions or even billions of years, gravity pulls inward while nuclear fusion pushes outward, and the two forces hold each other in a delicate cosmic equilibrium. From a distance, stars appear peaceful, almost eternal, glowing steadily against the darkness as though nothing could ever disturb them. But deep inside every massive star, there is a clock slowly counting down toward collapse. And unlike human clocks, this one does not tick in seconds or hours. It measures fuel. It measures pressure. It measures how long gravity can be held back before the star finally loses the battle it has been fighting since the moment it was born. A star far larger than our sun burns through its fuel with astonishing speed. The bigger the star becomes, the more violently its core must fuse atoms simply to support its own immense weight. A giant star 20 or 30 times heavier than the sun lives a strangely brief life compared to smaller stars. While our sun may shine for roughly 10 billion years, some massive stars exhaust themselves in only a few million. In cosmic terms, they live recklessly fast lives, burning brighter and dying younger. And near the end of that life, the star begins building heavier and heavier elements deep within its core. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. Layer after layer forms inside the star like the hidden rings of an ancient tree. But eventually the process reaches iron, and iron changes everything. Unlike lighter elements, iron does not release energy when fused. Instead, it consumes energy. The moment a massive star begins accumulating too much iron in its core, the balance that supported the entire star starts to fail. Fusion slows, outward pressure weakens, Gravity senses weakness immediately, and once gravity begins winning, it does not stop gently. The core collapses inward at a significant fraction of the speed of light, compressing more mass than our sun into a region no larger than a city. Temperatures rise into the billions. Electrons and protons are crushed together so violently that they merge into neutrons. Space itself begins behaving strangely under such extreme density. Matter no longer resembles anything familiar. A teaspoon of neutron star material would outweigh mountains on Earth. For many stars, this collapse creates a supernova, a colossal explosion that scatters heavy elements across surrounding space. But tonight our story follows the rare stars that descend even further into darkness. Some stars are simply too massive for even neutron matter to resist gravity forever. Their cores continue collapsing beyond the neutron star stage itself, falling inward until a black hole is born. And surrounding that newborn black hole is one of the strangest structures in the known universe, an accretion disk made of stellar material spiraling inward at nearly the speed of light. Imagine an ocean the size of a solar system collapsing toward a drain no wider than a city. The material cannot fall directly inward because it is rotating. Instead, it forms a flattened whirlpool of plasma heated to impossible temperatures. Magnetic fields twist violently through the disk like invisible tornadoes made of energy itself. Friction heats the gas until atoms are ripped apart completely. Radiation erupts outward in waves powerful enough to outshine galaxies. But even then, something even stranger begins to happen. The black hole and accretion disk together become an engine. Not an engine built from metal or machinery, but an engine of gravity, rotation, and magnetic chaos. Along the rotational poles of the black hole, narrow channels begin forming where energy can escape. Magnetic fields tighten and focus the escaping material into beams so concentrated that they resemble cosmic lighthouses piercing the universe. These beams are the beginning of a gamma-ray burst jet. And this is the crucial difference between an ordinary explosion and what we are exploring tonight. Most explosions spread their energy outward in every direction. A supernova radiates like a sphere expanding into darkness. But a gamma-ray burst does something terrifyingly different. It focuses almost all of its destructive power into an incredibly narrow beam. Instead of illuminating space evenly, it concentrates unimaginable energy into a corridor sometimes only a few degrees wide. It is the difference between a bonfire warming a field and a laser cutting through steel. The total energy may be similar, but the delivery mechanism transforms everything. Inside those jets, matter accelerates to more than 99.9% of the speed of light. At such velocities, Einstein's relativity dominates reality itself. Time behaves differently. Radiation compresses forward. The energy becomes concentrated into an almost impossibly intense stream moving across interstellar space. And for a brief moment, one dying star can appear brighter than every star in its galaxy combined. Yet even now, the true violence has not begun, because the jet is still trapped inside the dying star itself, surrounded by millions of miles of collapsing stellar material. Before the beam can reach open space, it must first carve its way outward through the star like a drill made of pure radiation. And what happens during that escape will transform the surrounding universe forever. Deep inside the collapsing star, The newborn jet is still imprisoned beneath millions of miles of stellar matter. From far away, the universe appears calm and silent, but within this dying giant, conditions have become almost incomprehensible. Temperatures exceed billions of degrees. Magnetic fields twist with unimaginable force. Entire layers of the star are falling inward while, at the same time, the jet attempts to blast outward. Two catastrophes are unfolding simultaneously inside the same object, one collapsing toward darkness, the other erupting toward freedom. The jet itself is not empty light. It is a torrent of particles, radiation, magnetic energy, and superheated plasma moving at velocities so extreme that ordinary intuition completely fails. If something traveled this quickly through Earth's atmosphere, the planet would not merely burn. The air itself would become a wall of nuclear fire. But inside the star, the jet encounters something even denser than any planetary atmosphere. It must force its way through layers of hydrogen, helium, carbon, oxygen, and heavier elements that once formed the internal structure of the massive star. And this journey outward is not smooth. The jet does not pass through the star like a clean beam through empty space. Instead, it tears, compresses, heats, and violently displaces stellar material as it advances. Imagine trying to fire a blowtorch through an ocean while the ocean itself collapses inward around the flame. Every second becomes a battle between outward pressure and collapsing gravity. The star resists the escape of the beam with enormous force. As the jet drills deeper, the surrounding stellar material is shoved sideways, forming a gigantic cocoon of superheated plasma around the beam. This cocoon becomes almost like a second explosion trapped within the star. It swells outward, pressing against the surrounding layers and helping clear a channel for the jet itself. The relationship becomes strangely cooperative. The jet powers the cocoon, and the cocoon stabilizes the jet. Together they carve a wound through the dying star. Computer simulations attempting to model this process require some of the most powerful supercomputers humanity has ever built, and even then, physicists struggle to fully understand the turbulence unfolding inside these collapsing giants. Relativistic fluid dynamics, magnetic instabilities, shock interactions, and radiation transport all combine into a chaotic storm of physics operating near the limits of modern understanding. Nature performs these calculations effortlessly while entire civilizations stare upward, trying to comprehend only fragments of what is happening. And not every jet succeeds. Some gamma-ray burst jets are too weak. Some stars are too massive. In those cases, the beam stalls before reaching the surface. All of its energy becomes trapped inside the star itself, inflating the cocoon until the entire star tears itself apart in an unusually violent supernova. Somewhere in the universe, there are failed gamma-ray bursts buried inside stellar explosions, hidden events where the engine tried to create a cosmic beam but never fully escaped its prison. But when the jet is strong enough, something extraordinary finally happens. After several seconds of tunneling through the stellar interior, the beam reaches the surface of the star and erupts outward into open space. This moment is the true birth of the gamma-ray burst. The instant the jet escapes confinement, radiation floods outward across the universe at the speed of light. A beam narrower than a finger held at arm's length suddenly carries more power than entire galaxies. And the environment outside the star is radically different from the crushing density within it. Inside the star, The jet struggled through matter thick enough to resist even relativistic motion. Outside, space is almost empty. The interstellar medium surrounding stars is so thin that, by earthly standards, it is a near-perfect vacuum. A few atoms per cubic centimeter drift silently between stars across unimaginable distances. The jet suddenly explodes into this emptiness like a hurricane emerging from underground confinement into open sky. It accelerates further. It expands slightly, and then it collides with the gas and dust surrounding the star. Massive stars often spend their final millions of years shedding enormous amounts of material into space through violent stellar winds. Long before the collapse begins, the star has already surrounded itself with shells of expelled gas stretching across light years. These clouds become the first victims of the emerging jet. When the relativistic beam slams into this surrounding material, the collision creates shock waves unlike anything familiar in ordinary life. The gas ahead of the shock has absolutely no time to react. Information inside matter travels at the speed of sound, but the jet approaches at nearly the speed of light. The surrounding gas cannot prepare, cannot move aside. One moment the region is cold and quiet, and the next it is consumed by a wall of catastrophic energy. The shock compresses matter to extraordinary densities. Temperatures leap into the billions of degrees. Atoms cease to exist as recognizable structures. Electrons are stripped away instantly, leaving only naked atomic nuclei suspended inside an ocean of plasma. Matter becomes so energetic that particles spiral through amplified magnetic fields and emit radiation across the electromagnetic spectrum, from radio waves to X-rays to the deadly gamma rays that first announce the burst itself. And this is where the real transformation of space begins, because the beam does not merely pass through the universe. It changes the universe wherever it touches. Molecular clouds are torn apart. Dust grains vaporize into plasma. Magnetic fields twist and amplify. Chemistry that may have taken millions of years to develop inside cold interstellar regions is erased in moments. Along the path of the jet, space itself is rewritten into something hotter, brighter, and infinitely more violent than before. The dying star is gone now. At the center remains only a black hole quietly feeding upon the final remnants of its former self. But far beyond that invisible darkness, the beam continues racing outward through the galaxy, carrying destruction across distances so vast that entire civilizations could vanish before ever understanding what reached them. By the time the jet has fully escaped the dying star, it has already transformed everything near its origin into an inferno of plasma and radiation. But strangely, the most frightening aspect of a gamma-ray burst is not simply the amount of energy involved. The universe contains many energetic events. Supernovas, quasars, even collisions between black holes all release astonishing power. What makes a gamma-ray burst uniquely terrifying is precision. It is violence focused into a direction. If a supernova is like a giant wave spreading outward across an ocean, then a gamma-ray burst is more like a spear. Its energy does not dissipate evenly across the cosmos. Instead, the beam carries destruction forward in a narrow corridor that can stretch across entire regions of a galaxy. And because the jet moves at relativistic speeds, another strange effect emerges from Einstein's theory of relativity itself. Radiation emitted inside the beam becomes compressed forward, concentrated even more tightly along the direction of motion. To anything standing directly in its path, the burst appears vastly brighter and more energetic than it otherwise would. Astronomers call this relativistic beaming, but the phrase sounds far gentler than the reality. Imagine every photon inside the jet being pushed forward into an ever tighter stream, as though the universe itself were squeezing light into a cosmic weapon. The result is that a dying star can briefly outshine hundreds of billions of stars combined. For a few silent seconds, a single point in space becomes brighter than an entire galaxy. And yet most gamma-ray bursts remain invisible to us. This is one of the strangest ideas in modern astronomy. The universe is likely filled with these explosions happening constantly across distant galaxies, but unless the beam happens to point almost directly toward Earth, we never see the event at all. Countless bursts may already have erupted in the cosmos while humanity slept peacefully beneath its skies, entirely unaware that somewhere far away, a star collapsed into catastrophic violence. This also means the universe is statistically far more dangerous than it appears. Because if the beam does happen to align with a planetary system, the effects become devastating across astonishing distances. A supernova generally threatens life only within a relatively local region of space. But a gamma-ray burst can remain dangerous for thousands of light years because its energy remains concentrated instead of dispersing evenly. Distance matters less when destruction is focused. As the jet races onward, it continues colliding with gas drifting between the stars. Each collision generates new shock fronts moving at nearly the speed of light. The gas ahead of these shocks has no ability to respond gradually. One moment it exists as cold interstellar matter floating quietly through darkness. The next moment it is compressed, heated, ionized, and accelerated into turbulence beyond comprehension. Behind the advancing shock wave, temperatures rise into ranges so extreme that ordinary chemistry completely disappears. Molecules are shattered apart instantly. Water vapor, carbon compounds, molecular hydrogen, every structure built through millions of years of cosmic chemistry is ripped into fragments. Even atomic nuclei themselves can begin breaking apart under the assault of ultra-energetic gamma radiation. This process, called photodisintegration, is one of the most violent interactions matter can experience outside the immediate edge of a black hole. Heavy elements forged deep inside stars over cosmic ages are torn apart again into smaller particles. The burst does not merely heat matter. It unbuilds it. Close enough to the beam, entire regions of space are chemically sterilized. Dust grains vaporize into plasma. Complex molecules vanish. The invisible architecture of cold nebulae dissolves into radiation-blasted emptiness. And because interstellar dust normally blocks light traveling through galaxies, the destruction of that dust creates strange transparent corridors through space. The burst effectively clears tunnels through surrounding material, allowing later radiation to travel even farther outward. Meanwhile, inside the shock front itself, particles are being accelerated to unimaginable energies. Charged particles bounce repeatedly across turbulent magnetic boundaries, gaining energy with each crossing until they become cosmic rays moving through the galaxy at nearly the speed of light. Some of the most energetic particles ever detected on Earth may have begun their journey inside ancient gamma-ray burst shocks billions of years ago. And these cosmic rays continue traveling long after the original burst fades from view. This is important because the gamma-ray burst is not truly a brief event. The initial flash may last seconds or minutes, but the aftermath unfolds across years, centuries, and even millennia. The shock wave continues expanding outward through interstellar space long after the black hole itself has gone quiet. The surrounding gas remains disturbed and superheated. Magnetic fields become tangled and amplified. Radiation echoes through the expanding debris field as the blast slowly decelerates. Astronomers call this lingering emission the afterglow. At first, the afterglow shines mostly in gamma rays and X-rays. Then, as the expanding shock loses energy, the light softens into ultraviolet radiation, visible light, infrared waves, and eventually radio emissions. The burst fades slowly across the electromagnetic spectrum like a wound in space cooling over time. Some afterglows remain detectable for years. And strangely, it was these fading afterglows that finally allowed astronomers to understand what gamma-ray bursts truly were. For decades after their discovery, scientists could detect the bursts themselves but had no idea where they originated. The flashes arrived suddenly and disappeared almost immediately, leaving no obvious trace behind. Some researchers even wondered whether the explosions might originate inside our own galaxy. But once telescopes learned to follow the fading afterglow, the truth became clear. These events were not local accidents inside the Milky Way. They were occurring billions of light-years away across the observable universe. And if they appeared this bright from such impossible distances, the true energy involved had to be almost beyond comprehension. Tonight, as we drift deeper into the story, remember something unsettling. Every gamma-ray burst we observe has already traveled across unimaginable gulfs of space before reaching us. Many erupted before Earth itself even formed. Some began their journey while the first stars in the universe were still young. And somewhere out there, perhaps even now, another massive star may already be collapsing into darkness, preparing to launch a beam that will continue racing silently through the cosmos long after humanity itself is gone. Long before humanity understood what gamma-ray bursts were, the universe had already been creating them for billions of years in silence. Ancient stars collapsed unnoticed in distant galaxies while their beams crossed intergalactic darkness like invisible arrows. Entire civilizations, if any ever existed beneath those distant skies, may have vanished without warning beneath storms of radiation arriving from stars they could not even see. And perhaps the strangest part of all is that the universe gives almost no advance notice before one of these events begins. A massive star nearing the end of its life can appear almost ordinary from a great distance. It shines brightly. It sheds stellar wind into surrounding space. It burns through its final fuel deep within its core, while nearby planets continue orbiting peacefully, unaware that gravity is preparing something catastrophic beneath the surface. Then suddenly, in less than a minute, the star collapses into a black hole and launches one of the most concentrated beams of energy nature can produce. For anything caught directly in the beam, there is no meaningful time to react. The radiation travels outward at the speed of light. Any warning arrives simultaneously with the destruction itself. A planet thousands of light-years away might spend millions of years developing oceans, atmospheres, ecosystems, perhaps even intelligent life, only to encounter a wall of gamma radiation that arrives without sound, without visible approach, and without mercy. But before we follow the beam toward worlds and civilizations, we need to understand one more important transformation happening inside the expanding jet itself. Because even after escaping the star and tearing through surrounding space, the beam does not remain stable forever. The universe slowly begins fighting back against it. As the relativistic jet plows through the interstellar medium, it continuously sweeps up gas and dust along its path. At first, the jet barely notices the resistance. Moving at more than 99% of the speed of light, it carries such overwhelming momentum that surrounding matter appears almost insignificant. But over time, the accumulated mass becomes enormous. The beam begins slowing very gradually, surrendering portions of its energy to the surrounding environment. And this transfer of energy changes the structure of the jet itself. At the front of the beam, shock waves continue compressing interstellar gas into intensely hot plasma. Behind the shocks, magnetic fields twist into turbulent knots. Electrons spiral through those fields and radiate enormous amounts of energy through synchrotron emission, producing the fading afterglow astronomers observe across the universe. Slowly, the narrow sphere of the burst begins broadening and weakening as its energy disperses outward into surrounding space. Yet even while weakening, the burst remains astonishingly destructive. The expanding shock front becomes a gigantic bubble of superheated plasma stretching across light years. Temperatures inside parts of the remnant remain millions of degrees for centuries. The once cold and quiet interstellar medium transforms into a violently disturbed region filled with accelerated particles, amplified magnetic fields, and turbulent radiation. In some places, the shock compresses nearby molecular clouds strongly enough to trigger the birth of entirely new stars. In others, it shreds those same clouds apart, preventing star formation altogether. Creation and destruction begin intertwining. This is one of the recurring patterns of the universe. Catastrophe rarely exists in isolation. The same explosion that sterilizes one region of space may seed another with the conditions necessary for future stars and planets. Heavy elements forged inside the collapsing star itself scatter outward through the galaxy. Carbon, oxygen, calcium, iron, all the ingredients needed for rocky worlds and biological chemistry are thrown back into interstellar space by stellar death. Somewhere far in the future, atoms created during one gamma-ray burst progenitor may eventually become part of another planetary system entirely, perhaps even part of another living creature. There is something strangely melancholic about this cosmic recycling. The universe destroys violently, but it also rebuilds endlessly from the remains. Meanwhile, the black hole left behind at the center of the burst settles into darkness. The accretion disk that once powered the jets gradually drains away. The engine that briefly outshone galaxies becomes quiet again, almost invisible against the surrounding void. If observers arrived thousands of years later, they might see only a faint remnant expanding silently through space, never suspecting the unimaginable violence that created it. But the universe remembers. The altered magnetic fields persist. Cosmic rays continue diffusing outward through the galaxy. Shock-heated gas glows faintly for ages. The burst leaves scars in space itself, traces of energy deposited across distances so vast that no human scale can properly visualize them. Entire corridors through the galaxy may remain chemically altered long after the original flash has faded beyond detection. And somewhere inside those disturbed regions, planets may continue orbiting their stars completely unaware that distant catastrophe once swept through nearby space. Because most worlds will never experience the full direct impact of a gamma-ray burst beam. Geometry matters enormously. A planet slightly outside the jet's path may survive with relatively minor consequences, while another directly aligned with the beam suffers extinction. The difference between survival and annihilation can depend on only a few degrees of alignment across thousands of light years. This directional nature makes gamma-ray bursts feel strangely personal compared to other cosmic disasters. A supernova expands outward broadly. An asteroid follows a trajectory shaped by gravity. But a gamma-ray burst resembles something disturbingly selective, almost like a cosmic searchlight moving across the galaxy. Most worlds never notice it. A few experience unimaginable devastation, and that raises an unsettling question. If gamma-ray bursts are capable of sterilizing planets across enormous distances, then how many worlds in the universe have already been erased by them? How many civilizations may have risen beneath peaceful skies only to disappear beneath radiation from a collapsing star far away? How many regions of the galaxy are simply too dangerous for complex life to survive for long periods of cosmic time? Because when we begin thinking about gamma-ray bursts not merely as explosions, but as filters acting across galactic history, the story becomes far larger than dying stars. It becomes a story about habitability itself, about whether advanced life can safely persist in a universe that occasionally fires concentrated beams of destruction across thousands of light years without warning. And that is where our journey moves next. Imagine a distant Earth orbiting quietly beneath a peaceful night sky. Oceans move gently beneath moonlight. Clouds drift above continents. Forests breathe slowly in darkness while an intelligent civilization, perhaps not unlike our own, studies the stars with curiosity and confidence. For millions of years, that planet may have existed in relative safety, protected by its atmosphere, its magnetic field, and the comforting assumption that space is mostly empty and calm. Then somewhere far away, a massive star dies. At first, nothing appears unusual. The doomed world continues spinning peacefully through space because the catastrophe is still crossing the gulf between stars at the speed of light. No alarm sounds across the planet. No visible object grows larger in the sky. The danger remains completely invisible during its journey. And that is part of what makes gamma-ray bursts so uniquely horrifying. Most natural disasters provide at least some warning. Earthquakes rumble. Hurricanes gather strength. Volcanoes tremble before eruption. But a gamma-ray burst arrives with almost supernatural suddenness. The first sign and the catastrophe itself are essentially the same event. Then the beam arrives. For a brief instant, the upper atmosphere of the planet absorbs an enormous flood of gamma radiation and X-rays. The atmosphere becomes the first shield standing between the surface and extinction. At first glance, this might sound reassuring. Earth's atmosphere protects us from harmful radiation every day. High-energy particles from the sun constantly strike the upper atmosphere and are harmlessly absorbed before reaching the ground. But a gamma-ray burst is not an ordinary source of radiation. The amount of energy involved exceeds anything Earth's atmosphere evolved to handle. The incoming gamma rays immediately begin ionizing atmospheric molecules on a massive scale. Nitrogen and oxygen atoms are ripped apart. Electrons are stripped away in violent cascades of radiation chemistry. The upper atmosphere transforms into an expanding layer of electrically charged plasma glowing with ghostly energy. For several terrifying moments, the sky itself becomes chemically unstable. One of the first major consequences is the rapid destruction of ozone. Normally, Earth's ozone layer quietly absorbs harmful ultraviolet radiation from the sun. It acts as an invisible protective filter high above the surface. But gamma radiation shatters nitrogen molecules apart, producing nitrogen oxides that begin destroying ozone far faster than natural systems can replace it. Within weeks or months after a sufficiently close gamma ray burst, a planet's ozone layer could collapse across enormous portions of the atmosphere. And the worst effects may not even happen immediately, because once the ozone shield weakens, ordinary sunlight itself becomes dangerous. Ultraviolet radiation from the planet's own star suddenly floods the surface with far greater intensity than ecosystems evolved to survive. Plants begin dying under increased radiation exposure. Oceanic plankton near the surface, responsible for huge portions of planetary oxygen production, suffer catastrophic losses. Food chains begin collapsing from the bottom upward. The terrifying irony is that after the gamma ray burst itself fades, the planet may look outwardly normal for some time. Oceans still move, mountains still stand, cities may even remain structurally intact. But the biosphere has been wounded in ways invisible at first glance. Radiation damage spreads slowly through ecosystems like poison dissolving into water. And if the burst is close enough, even worse effects begin unfolding. The atmosphere absorbs much of the initial radiation, but not perfectly. Some secondary particle showers reach the surface directly. High-energy electrons and other subatomic debris generated in the upper atmosphere cascade downward through the sky. Organisms exposed on the surface receive bursts of ionizing radiation capable of damaging DNA on enormous scales. Mutation rates rise dramatically. Sensitive species disappear first. Larger ecosystems destabilize gradually afterward. Meanwhile, the planet's atmosphere itself begins changing chemically. Nitrogen dioxide produced by the radiation can spread globally, creating brownish haze layers capable of partially blocking sunlight. Temperatures may drop. Weather systems become unstable. Acid rain increases as atmospheric chemistry spirals away from equilibrium. A planet may experience not only biological collapse, but climatic disruption as well. And all of this can happen from thousands of light years away. This is the part many people find difficult to emotionally process. Gamma ray bursts do not need to occur nearby in ordinary human terms. Space is vast, but these beams are extraordinarily focused. A burst occurring on the far side of a galactic spiral arm may still carry enough concentrated energy to seriously damage planetary atmospheres if alignment is unfortunate enough. Fortunately for Earth, long gamma ray bursts appear relatively uncommon inside mature galaxies like the modern Milky Way. The most dangerous bursts are usually associated with low metallicity environments where extremely massive stars form more easily. In other words, certain younger or chemically primitive galaxies may experience these events more frequently than our current region of space. Yet even so, astronomers cannot completely rule out the possibility that Earth has already experienced indirect effects from ancient gamma ray bursts sometime in its geological history. Some researchers have even proposed that one of Earth's past mass extinction events may have involved radiation from a relatively nearby gamma-ray burst. There is no definitive proof, but the idea remains scientifically plausible. A sufficiently close burst could damage the ozone layer severely enough to trigger widespread ecological collapse without leaving obvious impact craters or volcanic evidence behind. Life on the surface would simply begin dying beneath intensified solar radiation while the true cause remained hidden in deep space. And perhaps that possibility changes the way we think about extinction itself. When people imagine planetary destruction, they often picture explosions, impacts, or visible devastation. But the universe sometimes destroys more quietly. A gamma-ray burst may leave mountains untouched and oceans still glimmering beneath sunlight, while simultaneously dismantling the invisible atmospheric protections required for complex life to survive. A world can remain physically beautiful even while becoming biologically doomed. And somewhere tonight, beneath alien skies orbiting distant stars, there may already be planets unknowingly living through the first silent hours after such a beam has passed. There is another unsettling possibility hidden inside the story of gamma-ray bursts, and it reaches far beyond atmospheric chemistry or planetary extinction. It touches one of the oldest questions humanity has ever asked while staring into the night sky. If the universe is so vast, and if planets appear to be common, then where is everybody? This mystery is often called the Fermi paradox. By all reasonable estimates, the galaxy should contain enormous numbers of potentially habitable worlds. Many stars are billions of years older than the Sun. Some civilizations, if they emerged and survived, could theoretically possess technologies unimaginably beyond our own. And yet, when we listen to the stars, the universe remains strangely quiet. No confirmed signals, no visible galactic empires, no evidence of ancient civilizations spreading across the Milky Way. Only silence. Over the years, scientists and philosophers have proposed many explanations for this silence. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations destroy themselves through war or environmental collapse. Perhaps advanced species lose interest in communication. But gamma-ray bursts introduce another possibility, one rooted not in biology or sociology, but in astrophysics itself. What if parts of the universe are periodically sterilized before complex civilizations have enough time to spread? In the early universe, gamma-ray bursts were probably far more common than they are today. Young galaxies contained larger populations of massive low-metallicity stars, exactly the kinds of stars most likely to produce powerful relativistic jets. Entire regions of space may have experienced repeated bursts across cosmic history, bathing planets in radiation over and over again before advanced ecosystems could stabilize for long periods. In such a universe, the development of intelligent life becomes not merely a biological process, but a race against astrophysical catastrophe. A planet may require billions of years of relative environmental stability for intelligent civilizations to emerge. Complex multicellular organisms evolve slowly. Ecosystems become increasingly interconnected and delicate over geological time. But gamma-ray bursts care nothing for evolutionary progress. A sufficiently close beam could erase hundreds of millions of years of biological complexity in moments. This means certain regions of galaxies may effectively become dangerous zones for advanced life. Near dense star-forming regions where massive stars are abundant, gamma-ray bursts may occur too frequently for civilizations to survive long enough to become interstellar. Galactic centers may also be hazardous due to intense radiation environments and crowded stellar populations. In contrast, quieter outer regions of mature galaxies might provide longer windows of stability. Some scientists have even suggested that Earth's location within the Milky Way may not be accidental in this sense. Our solar system resides in a relatively calm region between major spiral arms, distant from the most active star-forming zones. We orbit a stable middle-aged star in a comparatively quiet neighborhood of the galaxy. Perhaps complex life survives more easily here because catastrophic events happen less often. If that idea is true, then habitability is not merely about liquid water or atmospheric chemistry. It is also about surviving the violence of the cosmos long enough for intelligence to evolve. And perhaps many worlds never get that chance. Imagine a planet where life repeatedly rises from the oceans over hundreds of millions of years, only to face periodic extinction from distant astrophysical events. Forests evolve, creatures diversify, intelligence begins emerging. Then suddenly, without warning, the atmosphere collapses beneath radiation from a gamma-ray burst originating thousands of light-years away. Ecosystems crash. Surface species vanish. Evolution begins again from surviving microbial life hidden underground or deep beneath oceans. The universe may contain countless interrupted worlds. And this idea becomes even stranger when we consider time itself. Gamma-ray bursts were more common billions of years ago when the universe was younger. As galaxies evolved chemically and massive low-metallicity stars became rarer, the frequency of long gamma-ray bursts appears to have declined. In other words, the modern universe may actually be safer for advanced life than the ancient cosmos once was. There may have been eras in cosmic history when galaxies were simply too violent for civilizations to endure. This creates a haunting possibility. Perhaps intelligent life across the universe is relatively young not because evolution is inherently slow, but because only recently have galaxies become calm enough for civilizations to survive without repeated sterilization events. If so, humanity may exist during a narrow cosmological window when the universe is finally settling into conditions suitable for long-term complexity. The silence of the stars may not mean civilizations never existed. It may mean many never lasted. And gamma-ray bursts are not the only threat. Supernovas, black hole activity, stellar flares, and galactic collisions all contribute to the dangerous ecology of the cosmos. But gamma-ray bursts remain especially terrifying because of their range and unpredictability. A civilization could carefully manage its climate, avoid war, and master advanced technologies, only to vanish beneath radiation from a star that exploded before their species even learned agriculture. The beam would arrive without negotiation, without intent, without malice, just physics. And perhaps that realization changes how we see ourselves. Humanity often imagines intelligence as something separate from nature, something capable of eventually controlling its destiny completely. Yet on cosmic scales, even advanced civilizations may remain fragile biological experiments suspended inside environments shaped by forces vastly older and more powerful than themselves. A gamma-ray burst reminds us that galaxies are not peaceful collections of stars. They are dynamic ecosystems of creation and destruction where entire worlds may live or die according to events unfolding thousands of light-years away. Still, there is another side to this story, because despite all this violence, life on Earth survived. Through asteroid impacts, supervolcanic eruptions, ice ages, solar storms, and mass extinctions, biology persisted. The universe is dangerous, yes, but it is also astonishingly resilient. Even after catastrophic collapses, life often begins rebuilding almost immediately. Microorganisms adapt. Ecosystems recover. Evolution continues experimenting again and again beneath changing skies. Perhaps somewhere in the galaxy, on worlds scarred long ago by radiation from ancient gamma-ray bursts, new oceans now shimmer peacefully beneath unfamiliar constellations. Perhaps entirely new evolutionary stories are already unfolding there tonight. And maybe that is the deeper truth hidden beneath all cosmic violence. The universe destroys endlessly, but it also creates endlessly. Stars collapse into black holes, yet their remnants seed future worlds. Radiation sterilizes planets, yet heavy elements forged in dying stars become part of future living creatures. Even catastrophe itself becomes part of the long machinery of cosmic renewal. Still, for any civilization staring nervously into the night sky, one unsettling fact remains impossible to ignore. Somewhere out there, another massive star is already nearing the end of its life. If a gamma-ray burst is one of the universe's most terrifying weapons, then the afterglow is its ghost. Long after the initial beam fades from visibility, the surrounding region of space continues carrying the memory of the explosion. Shock waves keep expanding. Magnetic fields remain tangled. Cosmic rays drift silently across the galaxy. Entire light years of interstellar space stay altered for ages beyond human comprehension. And in many ways, this lingering aftermath is even more fascinating than the burst itself, because it reveals how a single event can permanently reshape the environment around it. At first, the expanding shock front still moves at relativistic speed, sweeping outward like a wall of compressed plasma. The gas caught behind the shock becomes unimaginably hot, often reaching temperatures millions of times hotter than ordinary interstellar space. Electrons spiral through chaotic magnetic fields and emit synchrotron radiation that slowly changes color over time. X-rays fade into ultraviolet light. Ultraviolet fades into visible wavelengths. Visible light weakens into infrared glow and eventually into radio waves whispering across the cosmos years after the original explosion. To astronomers, these fading afterglows are priceless because they allow us to study events too distant and too violent to recreate anywhere else in nature. But from another perspective, the afterglow resembles a scar spreading through the galaxy. A region that was once cold, dark, and chemically stable has now been transformed into turbulent plasma threaded with amplified magnetic energy and flooded with high-energy particles. And these particles continue traveling astonishing distances. Cosmic rays accelerated by gamma-ray burst shocks may wander through galaxies for millions of years. Unlike light, which travels in straight lines, charged particles are constantly bent and redirected by magnetic fields. Their paths become tangled and chaotic. Some eventually collide with planets. Some enter molecular clouds where future stars are forming. Some may still be crossing interstellar space from explosions that occurred before Earth even existed. There is something haunting about that idea. At this very moment, tiny subatomic particles from ancient stellar catastrophes may be passing through your body silently, remnants of explosions that happened billions of years ago in distant galaxies. The universe is filled with invisible echoes. Inside molecular clouds, these cosmic rays can alter chemistry in surprisingly important ways. Deep within dense clouds of gas and dust where ordinary starlight cannot penetrate, cosmic rays remain one of the few energy sources capable of triggering chemical reactions. They ionize atoms. They break molecular bonds. They help create complex organic compounds drifting through interstellar space. Some scientists believe cosmic rays may play a role in producing ingredients connected to prebiotic chemistry itself. And this creates one of the strangest paradoxes in the entire story of gamma-ray bursts. The same explosions capable of sterilizing planets may also contribute indirectly to the chemistry needed for future life elsewhere. Again and again, the universe refuses to separate destruction from creation. They arrive intertwined. As centuries pass after the burst, the relativistic shock gradually slows into something more similar to an enormous supernova remnant. The expanding shell continues sweeping through interstellar space, collecting gas and dust while spreading its energy across larger and larger volumes. Over thousands of years, the remnant may grow across dozens of light years, becoming an immense bubble of hot plasma suspended inside the galaxy. Within that bubble, the magnetic environment remains permanently altered. Before the burst, magnetic fields may have drifted gently through the interstellar medium in relatively ordered patterns shaped by galactic rotation and stellar winds. After the burst, turbulence twists those fields into chaotic structures. Gas clouds respond differently. Star formation patterns shift subtly. The architecture of surrounding space changes. And these effects can outlive civilizations. Human history spans only a few thousand years. Recorded astronomy covers barely a fraction of that. Yet the environmental consequences of one gamma-ray burst can persist across time spans longer than all of human civilization combined. By the time the disturbed region finally relaxes back toward ordinary galactic conditions, species may rise and disappear many times over on distant planets. This is one reason the universe feels both beautiful and emotionally difficult to comprehend. Human lives unfold on scales of decades, while astrophysical processes continue unfolding across millions of years with complete indifference to individual existence. A gamma-ray burst may begin before Earth develops multicellular life and still influence galactic environments long after humanity vanishes. And yet somehow, despite these scales, we have learned to understand pieces of it. Tiny creatures living on a small rocky planet around an ordinary star have discovered how black holes launch relativistic jets across the cosmos. We have mapped afterglows from billions of light years away. We have traced the signatures of exploding stars older than our species itself. There is something deeply moving about that achievement. The universe may be violent and indifferent, but consciousness still emerged within it capable of asking questions about its origins. Perhaps that is part of the cosmic story too. Not only destruction, not only collapse, but awareness. And awareness changes how we experience the night sky. Once you understand gamma-ray bursts, the stars no longer seem entirely peaceful. Hidden among those distant points of light are massive stars nearing collapse. Some already contain the seeds of future black holes inside their cores. Some are rotating rapidly enough to produce relativistic jets when they finally die. Somewhere in the Milky Way tonight, there are stars quietly approaching the final minutes of lives that lasted millions of years. Yet from Earth they appear calm. That contrast between appearance and reality exists everywhere in the cosmos. Galaxies look serene from afar while black holes rage inside their centers. Nebulae glow softly while shock waves tear through them. Even our own atmosphere appears tranquil despite constantly shielding us from radiation streaming through space. The universe is filled with hidden violence concealed beneath beauty. And perhaps gamma-ray bursts reveal that duality more clearly than any other phenomenon. They are horrifying events, yet visually magnificent. They destroy worlds, yet forge elements needed for future life. They remind us of cosmic fragility, yet also demonstrate the astonishing resilience of matter and evolution. Eventually, the afterglow fades almost completely. The shock merges gradually into the ordinary turbulence of the galaxy. The burst becomes history. Future stars form from gas enriched by the remains of dead ones. New planets emerge. New skies appear above future oceans. But somewhere far away, another star has already begun collapsing. And another beam is already preparing to cross the darkness. There is a quiet moment that comes after studying phenomena like gamma-ray bursts for long enough. At first, the mind reacts with fear and awe. The scales are too enormous. The violence feels impossible. Entire planets can be damaged from thousands of light years away by beams launched from collapsing stars. Black holes form in seconds. Space itself becomes flooded with radiation capable of dismantling atoms and rewriting chemistry across entire regions of galaxies. Everything feels unstable beneath such knowledge. But eventually another feeling begins emerging beneath the fear. Perspective. Because gamma-ray bursts also reveal how extraordinarily rare and fragile our existence truly is. Earth has survived for billions of years beneath a sky filled with hidden dangers. Through pure cosmic fortune, our planet appears to occupy a relatively calm era and region of the Milky Way. The sun is stable. Nearby stars are mostly quiet. No relativistic jet currently points toward us from a nearby collapsing giant. Life has been given enough uninterrupted time to evolve complexity, intelligence, memory, curiosity, and eventually astronomy itself. That realization changes the emotional meaning of the night sky. The stars no longer feel permanent or harmless, but they also become more precious. Every calm night above Earth represents stability won against astronomical odds. Every living ecosystem on this planet exists because countless catastrophic possibilities did not happen at the wrong moment. Humanity inherited a rare window of cosmic quiet, and within that quiet we learned how to look outward and understand the forces surrounding us. And perhaps that is why gamma-ray bursts fascinate us so deeply. They force us to confront both our vulnerability and our uniqueness at the same time. A civilization living beneath a peaceful atmosphere can easily begin believing itself separate from the cosmos. Cities glow brightly enough to hide the stars. Technology creates illusions of control. Human concerns shrink inward toward politics, economics, and personal struggles. Yet one glance at a gamma-ray burst reminds us that civilizations are ultimately biological events unfolding inside a much larger astrophysical environment. We are not outside the universe observing it safely from a distance. We are inside it. The oxygen in our blood came from ancient exploding stars. The iron in Earth's core formed during stellar collapse long before the sun existed. Even the atoms inside our nervous systems were assembled through nuclear reactions deep within stars that died billions of years ago. And somewhere in the future, those same atoms will eventually scatter back into space again. Gamma ray bursts simply reveal this cycle in its most dramatic form. A massive star lives briefly, dies violently, launches jets across the galaxy, enriches surrounding space with heavy elements, disturbs magnetic fields, triggers new star formation, and leaves behind a black hole drifting silently through darkness. Then from the remains, new stars emerge, new planets form, new chemistry begins. Perhaps eventually new life appears beneath those future skies and asks the same questions we ask now. The universe is terrifying, yes, but it is also deeply continuous. Nothing truly remains isolated forever. Even black holes, which seem like ultimate endings, still influence their surroundings through gravity and energy. Even gamma ray bursts, despite their destructive power, become part of larger cosmic renewal. The galaxy recycles catastrophe into possibility over and over again. And this endless recycling may explain why the universe feels both ancient and strangely alive at the same time. Galaxies evolve almost like ecosystems. Stars are born, age, die, and seed future generations. Regions of space become temporarily dangerous and later peaceful again. Matter migrates endlessly through different forms across cosmic time. Tonight, somewhere beyond the visible stars above Earth, there are probably worlds orbiting quietly beneath unfamiliar constellations. Some may be barren. Some may contain oceans beneath frozen crusts. Some may host primitive life hidden beneath seas or underground rock. And perhaps a few may already possess civilizations staring upward in wonder exactly as we do. Some of those civilizations may survive for millions of years. Others may disappear silently beneath astrophysical catastrophes before ever leaving their home systems. And none of them, no matter how advanced, can fully escape the laws governing the cosmos around them. There is something oddly peaceful in accepting that truth. Not hopelessness, not fear, simply perspective. The universe is not cruel in the human sense because it has no intention. Stars collapse because gravity demands it. Black holes form because mass curves space-time. Gamma ray bursts erupt because energy follows physical law. The cosmos does not choose victims. It simply unfolds according to processes older than galaxies themselves. And still, despite all that indifference, consciousness emerged. Tiny self-aware creatures learned to map explosions occurring billions of light years away. We discovered relativity. We detected afterglows fading across the universe. We built instruments capable of studying the deaths of stars older than Earth itself. Somehow, inside all this violence, the universe produced beings capable of understanding fragments of its own story. Perhaps that is one of the rarest events of all. So tonight, as the afterglow finally fades into darkness and the expanding shock dissolves slowly into the galaxy, let the scale of it settle gently into your thoughts. Somewhere far away, a black hole drifts silently where a giant star once lived. Around it, disturbed gas still glows faintly across light years of space. Magnetic fields remain twisted from ancient turbulence. Cosmic rays continue wandering through the galaxy carrying echoes of a catastrophe long past. And here on Earth, beneath a calm atmosphere protected for now from such violence, we continue listening to the universe. The stars above us appear peaceful tonight. Their light drifts softly through darkness exactly as it has for countless generations. But hidden among them are engines of unimaginable power, sleeping giants slowly approaching collapse, future black holes waiting inside stellar hearts. And yet the night remains beautiful anyway. Maybe that is the final lesson of gamma ray bursts. The universe is not beautiful because it is safe. It is beautiful because even within unimaginable violence, stars still shine, worlds still form, life still emerges, and somewhere in the silence between galaxies, consciousness still opens its eyes and wonders. If there is one final illusion that gamma ray bursts destroy completely, it is the idea that space is empty. From Earth, the void between stars appears silent and motionless, a vast darkness interrupted only by distant points of light. But the deeper astronomy looks into the universe, the more active and turbulent that darkness becomes. Space is filled with radiation, magnetic fields, drifting molecular clouds, shock waves from ancient explosions, and invisible streams of particles crossing galaxies for millions of years. Even now, while Earth sleeps beneath calm skies, the universe is alive with hidden movement, and gamma ray bursts are among the most dramatic reminders of that invisible activity. They reveal that galaxies are not static structures. They are ecosystems shaped by cycles of collapse and renewal. Massive stars form inside dense clouds of gas, burn briefly with terrifying intensity, and then die in ways capable of altering entire regions of space around them. The resulting black holes continue drifting through the galaxy, while the energy released during their birth reshapes surrounding matter across enormous distances. Yet strangely, most of these events unfold in complete silence. A gamma ray burst occurring thousands of light years away would not create thunder or visible explosions in the sky. The radiation would arrive soundlessly. The atmosphere would begin changing invisibly. Ecosystems would weaken gradually beneath altered chemistry and increased ultraviolet exposure. Even extinction itself might unfold quietly over years rather than moments. Entire worlds could become biologically wounded before fully understanding what had happened to them. There is something deeply unsettling about a disaster that leaves no obvious crater behind. And perhaps that silence mirrors the universe itself. Cosmic violence is often hidden beneath extraordinary beauty. Nebulae glow softly while shock fronts tear through them. Spiral galaxies rotate elegantly while black holes feed at their centers. Even the night sky above Earth feels calm despite containing stars powerful enough to sterilize planets if circumstances align differently. The universe rarely announces danger in emotionally recognizable ways. Instead, it simply follows physics. For humanity, this realization carries both humility and wonder. We evolved on a small rocky world orbiting an ordinary star, yet we now understand processes unfolding across billions of light years. We know how stars collapse. We know how relativistic jets form around black holes. We can measure afterglows fading through the cosmos from explosions older than human civilization itself. Against all odds, matter became conscious enough to study the machinery that created it. And perhaps that achievement is more fragile than we sometimes realize. Human civilization often measures itself against centuries. Nations rise and fall. Languages evolve. Technologies transform daily life within generations. but astrophysical events operate on scales that make civilizations appear almost temporary. A gamma-ray burst may spend billions of years crossing the universe while entire species emerge and disappear during its journey. Even galaxies evolve slowly compared to the brief span of intelligent life. Still, fragility does not mean meaninglessness. In fact, gamma-ray bursts may make conscious existence feel more extraordinary rather than less. The universe is not obligated to produce stable worlds. It is not designed for comfort. Yet somehow, amid all the collapse, radiation, and gravitational violence, planets like Earth still emerge. Oceans still form. Life still persists long enough to become aware of the stars surrounding it. Perhaps that rarity is what makes awareness valuable. Somewhere tonight, there may be civilizations looking upward from distant planets, wondering whether they are alone beneath their skies. Some may already understand gamma-ray bursts and fear them. Others may not yet possess astronomy advanced enough to recognize the danger. A few may even exist inside regions of the galaxy where long-term survival is statistically unlikely due to nearby star formation activity. And somewhere else, there may be dead worlds orbiting peacefully beneath silent stars, their atmospheres stripped long ago by radiation from ancient cosmic explosions. The galaxy may contain both stories simultaneously. This duality appears everywhere in astronomy. Regions of destruction become regions of creation. Stellar death seeds future planetary systems. Black holes generate jets that trigger new star formation elsewhere. Even extinction events can redirect evolution toward entirely different futures. The cosmos behaves less like a machine moving toward one outcome and more like an endless unfolding of interconnected transformations. Nothing stays unchanged forever. Even the gamma-ray burst itself eventually disappears completely. The afterglow fades into darkness. The blast wave merges into ordinary interstellar turbulence. Future stars form from the remnants. Future planets condense from enriched dust. Given enough time, even the scars of catastrophe dissolve back into the galaxy. But traces always remain. The heavy elements forged inside collapsing stars continue traveling through space. Cosmic rays still drift invisibly through magnetic fields. Black holes persist silently long after their violent births are forgotten. And somewhere inside future living organisms, atoms from ancient explosions may become part of new minds asking ancient questions again. Where did we come from? Are we alone? How dangerous is the universe? And perhaps the deepest question of all, how can something as violent as the cosmos still produce beauty? Maybe the answer lies in scale. Human beings naturally experience existence locally. We feel storms, seasons, personal memories, and individual lives. But the universe operates across scales so enormous that destruction and creation become inseparable parts of one continuous process. Stars must die for heavier elements to exist. Explosions must scatter those elements across galaxies. New stars and planets must form from ancient remains. Without collapse, there would be no renewal. Without stellar death, there would be no Earth. And without the terrifying forces we explored tonight, there would be no conscious beings capable of gazing upward in wonder at all. So as our journey slowly drifts toward its final quiet descent, let yourself hold both truths at once. The universe is dangerous beyond ordinary comprehension. Gamma-ray bursts can sterilize worlds, reshape galaxies, and erase biological histories in moments. Yet the same universe also creates stars, oceans, atmospheres, ecosystems, memory, curiosity, and thought. Violence and beauty were never separate things in the cosmos. They were always part of the same story. Perhaps the strangest thing about gamma-ray bursts is that, despite all their unimaginable violence, the universe barely notices them afterward. Galaxies continue rotating. Stars continue forming. Nebulae continue glowing softly across interstellar darkness. Even after one of the most energetic events in existence erupts across space, the larger cosmos carries on almost undisturbed. The scale of the universe is so immense that even catastrophe on this level becomes only one brief chapter in an endless cosmic story. And maybe that realization feels both comforting and unsettling at the same time. Human beings naturally place enormous emotional weight on destruction because our lives are short and fragile. A single disaster can define generations. Entire civilizations remember wars, extinctions, and collapses for thousands of years. But galaxies operate across scales where millions of years pass like weather. Stars die constantly, black holes merge, radiation storms cross interstellar space. Matter reorganizes itself endlessly into new forms. The cosmos does not cling to permanence. Yet despite that constant change, patterns endure. Gravity continues gathering gas into stars. Nuclear fusion continues illuminating darkness. Chemistry continues building complexity from simple elements. Life, wherever conditions permit it, may continue emerging again and again despite the dangers surrounding it. This resilience may be one of the most important truths hidden beneath the story of gamma-ray bursts. Because when we first encounter these explosions, they appear almost overwhelmingly destructive. Beams capable of sterilizing planets feel incompatible with fragile ecosystems and conscious life. But Earth itself already exists as proof that survival through cosmic danger is possible. Our planet formed in a universe already filled with supernovas, radiation, and collapsing stars. Every atom around us has survived previous cycles of astrophysical violence before becoming part of oceans, mountains, forests, and living cells. In a strange way, life is not separate from cosmic catastrophe. Life is partly made from its remains. The calcium inside bones, the oxygen in every breath, the iron carried through blood, all were forged in ancient stars that ended their lives violently. Even black holes and gamma-ray bursts participate indirectly in the long chain of events leading toward future worlds. Stellar collapse enriches galaxies with heavy elements. Shock waves compress gas clouds into new star-forming regions. Radiation alters chemistry across interstellar space. Destruction becomes transformation, and transformation appears to be the true language of the cosmos. Nothing remains fixed forever. Not stars, not planets, not civilizations. Even galaxies themselves eventually collide and merge across billions of years. The night sky visible above Earth tonight will not look the same forever. Constellations slowly drift apart. The Milky Way and Andromeda are already falling toward one another through space, destined to merge in the unimaginably distant future. Against such scales, human history becomes almost impossibly brief. Yet perhaps brevity is not weakness. In some ways, Temporary things become more meaningful precisely because they do not last forever. A sunset matters because it fades. A human life matters because it is limited. Civilizations matter because they are fragile achievements carved from chaos and uncertainty. Gamma ray bursts remind us that existence was never guaranteed. Somewhere else in the universe, there may have been worlds very much like Earth that never received enough stable time for intelligence to emerge. Some may have lost their oceans beneath runaway radiation. Others may have endured repeated extinction events that prevented complex ecosystems from stabilizing. There may even have been civilizations more advanced than ours erased long before humanity evolved. We simply do not know. The silence of the cosmos leaves enormous room for possibility. And perhaps that uncertainty is part of what makes astronomy feel almost spiritual at times. Every observation becomes both scientific and philosophical. Every distant galaxy contains histories we cannot fully imagine. Every star may possess worlds carrying unknown stories beneath alien skies. And among all those stars, some are still preparing to die. Right now, deep inside certain massive stars, gravity is slowly winning. Iron accumulates inside stellar cores. Nuclear fusion weakens. Rotational energy builds. Invisible magnetic fields twist through plasma heated beyond comprehension. Somewhere tonight, perhaps in another spiral arm of the Milky Way, a giant star may already be approaching the final minutes of a life lasting millions of years. Sooner or later, the balance will fail. The core will collapse inward faster than human intuition can properly visualize. A black hole will form. Jets will erupt outward at relativistic speeds. Radiation will burst across the galaxy carrying more energy in seconds than our sun will release across its entire lifetime. And the universe will continue onward almost calmly afterward. That quiet indifference is difficult for the human mind to accept at first, but there is also peace hidden within it. The cosmos does not hate. It does not target. It simply evolves according to physical law. Stars collapse because gravity bends space-time. Jets form because rotating magnetic fields channel energy into narrow beams. Galaxies change because matter responds to gravity across immense spans of time. No anger, no cruelty, only process. And inside those processes, consciousness briefly awakens. Perhaps that is the true miracle hidden in the darkness. Not that the universe is safe, but that awareness exists within it at all. Tiny living beings on small planets learned how to measure radiation from ancient explosions billions of light years away. We learned how to decode the deaths of stars from faint afterglows drifting through space. We became capable of understanding pieces of the universe that created us. Tonight, as the stars continue shining softly above Earth, let yourself rest inside that perspective for a moment. The cosmos is vast beyond comprehension. It contains violence powerful enough to erase worlds and timescales so enormous that civilizations appear like sparks in darkness. Yet somehow, within all that immensity, there is still room for oceans, forests, memory, music, thought, curiosity, and wonder. And maybe wonder itself is one of the rarest things the universe has ever produced. Maybe the most haunting aspect of gamma ray bursts is not their power, but their invisibility. If one occurred close enough to threaten Earth, most people would never see a dramatic explosion in the sky. There would be no flaming object descending toward the planet. No giant shockwave crossing the horizon. The danger would arrive hidden inside light itself, buried within radiation moving silently across the galaxy at the speed of light. The atmosphere would absorb the first impact high above the surface where no human eye could witness it directly. Invisible chemical reactions would begin unfolding in the upper sky while oceans continued moving peacefully below. Cities would remain illuminated. Forests would still sway in the wind. For a short time, the world might appear completely normal even as the foundations protecting life slowly began to fail. There is something deeply eerie about a catastrophe unfolding invisibly overhead while ordinary life continues beneath it unaware. And perhaps that image captures something larger about existence in the universe. Much of reality remains hidden from direct human senses. We cannot naturally see gamma rays, magnetic fields, cosmic rays, space-time curvature, or black holes. Yet these invisible processes constantly shape the cosmos around us. Astronomy has taught humanity that the visible universe is only a small surface layer covering much deeper structures and forces operating silently beneath appearances. Gamma-ray bursts pull back that curtain for a moment. They reveal how quickly stability can vanish on cosmic scales. A star may spend millions of years appearing steady and eternal before collapsing in seconds into one of the most violent events nature can create. Entire planetary biospheres may depend on atmospheric balances delicate enough to be disrupted by radiation from distant galaxies. Civilizations may rise believing themselves secure while remaining vulnerable to forces unfolding far beyond their awareness. And still, despite all this fragility, life continues appearing. That persistence may be one of the most extraordinary things in existence. The universe does not provide easy conditions for complexity. Most of space is lethally cold, airless, and irradiated. Stars explode. Black holes consume matter. Planets freeze, burn, collide, or lose their atmospheres. Yet against all those odds, chemistry repeatedly organizes itself into living systems capable of adaptation and memory. Perhaps life survives not because the universe is gentle, but because life itself is resilient. Even on Earth, extinction has never been absolute. Asteroid impacts ended dynasties of species, yet ecosystems eventually recovered. Ice ages transformed climates, yet organisms adapted. Volcanic catastrophes darkened skies, yet biology persisted through each collapse. The history of life is not a story of uninterrupted peace. It is a story of survival through instability. In that sense, gamma-ray bursts become part of a much older cosmic rhythm. Catastrophe reshapes environments, and evolution responds. Some branches disappear forever. Others adapt to new conditions. Over immense spans of time, complexity returns again and again like waves reforming after storms. And maybe civilizations are not exceptions to that pattern. Humanity often imagines technological progress as a path toward permanent security, yet astronomy humbles that assumption repeatedly. No amount of engineering changes the laws governing stars and galaxies. Even an advanced civilization cannot stop a black hole from forming inside a collapsing stellar core thousands of light-years away. Intelligence may reduce certain dangers while remaining vulnerable to others vastly larger than itself. But perhaps the goal of intelligence was never absolute control. Perhaps consciousness exists not to conquer the cosmos, but to witness it, to understand it, to experience wonder inside it despite uncertainty. There is something profoundly meaningful about fragile beings studying a universe capable of destroying them. It suggests curiosity itself may be one of the rarest and most beautiful outcomes of cosmic evolution. And curiosity changes fear into perspective. Once we understand gamma ray bursts, they stop feeling like mythical punishments from the sky and instead become chapters in the natural history of galaxies. Terrifying chapters, certainly, but understandable ones. We know how relativistic jets form. We know how afterglows evolve. We know how radiation alters atmospheres and magnetic fields. Knowledge does not remove danger, but it transforms panic into awareness. Humanity has always done this. Ancient eclipses once inspired terror until astronomy explained orbital motion. Comets were treated as omens until celestial mechanics revealed their paths. Lightning once appeared supernatural until physics uncovered electricity. Again and again, understanding transformed fear into connection with the universe rather than separation from it. Gamma ray bursts continue that tradition. The more we learn about them, the more they stop feeling like alien interruptions and instead become recognizable expressions of cosmic law. Gravity collapses matter. Rotation channels energy. Magnetic fields shape plasma. Relativity focuses radiation into beams crossing interstellar darkness. The processes are extreme, but they remain part of the same universe that also produces calm sunsets, ocean tides, snowfall, and quiet starlight. Perhaps the cosmos was never divided between peaceful beauty and violent destruction. Those were always human categories imposed upon a universe operating as one continuous whole. And tonight, beneath Earth's atmosphere, we remain suspended safely within a temporary region of stability inside that larger process. The stars above us glow softly across the darkness exactly as they did for ancient civilizations long before telescopes existed. Yet now we understand that hidden among those distant lights are collapsing giants, black holes, shock waves, and radiation storms unfolding silently across the galaxy. The night sky became more dangerous once astronomy advanced. But it also became infinitely more profound, because now we know that every calm star overhead is part of a much larger cosmic story stretching backward across billions of years. We know the atoms inside our bodies were forged inside ancient stellar interiors. We know some distant black holes were born from explosions so energetic they temporarily outshone galaxies. And we know that despite all this violence, consciousness still emerged capable of gazing upward and asking questions about its origins. That may be the strangest outcome of all. The universe created beings able to contemplate the universe itself. Now the journey grows quiet. Far beyond Earth, the afterglow of some ancient gamma ray burst is still fading through interstellar darkness. A shock wave continues expanding across forgotten regions of a distant galaxy. Magnetic fields remain tangled from turbulence born thousands of years earlier. Somewhere, a black hole drifts silently where a giant star once burned with impossible brightness. And around all of it, the universe continues onward in its vast and patient rhythm. Galaxies rotate slowly through darkness. New stars ignite inside cold molecular clouds. Old stars collapse and disappear. Radiation crosses unimaginable distances in silence. Everything moves. Everything changes. And yet, from the perspective of a human life, the night sky can still feel timeless. Perhaps that is why astronomy affects us so deeply. It stretches the mind across scales almost too large to emotionally contain. A gamma ray burst may last only seconds, yet its consequences echo across millions of years. A black hole may form instantly, yet drift through the galaxy longer than entire civilizations survive. Human beings live briefly inside processes so immense that even stars appear temporary. And still we look upward. That instinct to look toward the cosmos may itself be one of the most extraordinary things in existence. Long before modern science, human beings sat beneath dark skies wondering what the stars truly were. Ancient cultures imagined gods, spirits, fires, and celestial oceans above them. Today we know those lights are suns, galaxies, neutron stars, and black holes scattered across distances so vast that language struggles to describe them properly. Yet strangely, understanding the science has not removed the wonder. If anything, it deepened it, because reality turned out to be far stranger and more beautiful than mythology ever imagined. Somewhere tonight, massive stars are nearing the end of their lives. Deep inside their cores, gravity slowly gains strength while fusion weakens. Invisible magnetic fields twist through collapsing plasma. In time, some of those stars will vanish into black holes and launch beams of radiation across the universe. Entire regions of surrounding space will transform beneath relativistic shockwaves and expanding afterglows. Matter will be broken apart and rebuilt again into future stars and future worlds. And perhaps on one of those future worlds, another civilization will eventually emerge beneath unfamiliar constellations. Maybe they too will study the cosmos and discover gamma-ray bursts. Maybe they will feel the same mixture of awe and fragility humanity feels tonight. Maybe they will understand that existence is temporary, yet still profoundly meaningful precisely because it is temporary. Or perhaps the universe will remain silent there, carrying only drifting oceans beneath empty skies. We do not know, and there is humility in accepting that uncertainty. Astronomy reveals astonishing truths about the cosmos, but it also reminds us how much remains hidden. Dark matter still surrounds galaxies invisibly. Consciousness itself remains mysterious. Countless worlds orbit distant stars beyond direct observation. The universe is not a puzzle humanity has solved. It is an ocean we have only just begun exploring. Gamma-ray bursts are simply one glimpse into that deeper reality. One reminder that beneath the calm appearance of the stars lies a cosmos filled with energies and scales beyond ordinary imagination. Yet they are also reminders of continuity. The same laws creating black holes also created atoms, planets, oceans, and life. The same stellar deaths capable of sterilizing worlds also forged the heavy elements inside every living creature on Earth. We are children of ancient stars studying the deaths of stars. And perhaps that realization is quietly comforting in its own way. Even in a universe capable of tremendous violence, there remains connection. The atoms inside your body were once part of exploding suns. The calcium in your bones traveled through interstellar space before Earth formed. Every breath contains material older than the solar system itself. Human beings are not strangers inside the cosmos. We are expressions of it. For a brief moment in cosmic time, the universe became aware enough to observe itself through human eyes. Tonight, as you rest beneath Earth's atmosphere, The galaxy continues moving around you. The Milky Way turns slowly through darkness, carrying billions of stars across space. Some are young, some are ancient, some already collapsed long ago into black holes invisible against the void. And hidden somewhere among them are future gamma-ray bursts waiting patiently inside stellar hearts. But for now, our sky remains calm. The atmosphere still protects the oceans below. The magnetic field still shields the planet from cosmic radiation. Forests still breathe quietly beneath moonlight. Cities glow softly across continents, while countless people sleep unaware of the immense cosmic machinery surrounding them. There is peace in that ordinary moment. And maybe peace becomes more meaningful once we understand how rare and fragile it truly is. So let the universe feel vast tonight. Let it feel mysterious. Let the stars remain beautiful, even knowing the hidden violence they sometimes contain. Because beauty in the cosmos was never the absence of danger. Beauty was always the coexistence of fragility and endurance, silence and explosion, collapse and renewal. Far away, an ancient afterglow fades slowly into darkness. A black hole drifts through the remains of a dead star. Radiation from forgotten explosions continues crossing the universe unseen. And here on Earth, beneath quiet skies, consciousness continues wondering about it all. The stars are still shining. The galaxy is still turning. And the universe, immense and restless and beautiful beyond comprehension, continues dreaming in the dark, bottom of form,